Quantum entanglement is often described as one of the most mysterious and mind-bending phenomena in all of physics. To truly appreciate it, one must first understand that it defies almost everything we instinctively believe about the way the world works. From childhood, we are taught that objects are separate from one another, that what happens here cannot instantly affect something across the room, much less across the universe. Our daily experience tells us that if I drop a glass on the floor, it shatters here and now. It doesn't cause a vase in another city to break at the same time. Cause and effect follow predictable patterns, limited by space and time. Yet quantum entanglement suggests that nature itself doesn't fully obey those rules, and at the deepest level of reality, things are more connected than we can see. Entanglement occurs when two or more particles, such as photons, electrons, or atoms, interact in such a way that their properties become linked. Once entangled, the state of one particle is directly tied to the state of the other, no matter how far apart they are separated. If you measure one, you instantly know something about the other. Imagine two coins flipped into the air. In a classical world, each coin lands randomly on heads or tails, and the outcome of one has no effect on the other. But in the quantum world, if those coins are entangled, then once you observe one as heads, the other is guaranteed to be tails, even if it's on the opposite side of the galaxy. And this correlation happens instantaneously, without anything traveling between them in the conventional sense. It's as though they share a hidden connection that transcends space and time. This idea is difficult to grasp because it conflicts with the principle of locality, the common sense notion that objects are only directly influenced by their immediate surroundings. Locality insists that information cannot travel faster than the speed of light, a limit set by Einstein's theory of relativity, but entanglement seems to mock this law. If the outcome of one particle instantly determines the outcome of another far away, doesn't that mean information is somehow moving faster than light? Scientists debated this for decades, with Einstein himself resisting the idea. He suspected there must be hidden variables, undiscovered factors that predetermine the outcomes, making the phenomenon appear stranger than it really was. Yet, as the decades rolled on and more sophisticated experiments were conducted, those hidden variables were ruled out. The evidence became overwhelming. Entanglement is not an illusion. It is a genuine feature of reality. One of the most compelling demonstrations came through experiments inspired by the work of physicist John Bell in the 1960s. Bell formulated a test, now known as Bell's theorem, that could determine whether entangled particles behaved in a way that supported Einstein's local hidden variable theory, or in a way that supported the strange predictions of quantum mechanics. Over time, countless experiments around the world confirmed the quantum predictions. Entangled particles behaved as though they were linked instantly, no matter the distance. Scientists sent entangled photons miles apart, separated by mountains, cities, and even to orbiting satellites in space. Every time the results held true. No signal seemed to pass between the particles, yet they acted in perfect correlation. The mystery only deepened, but what is truly remarkable about entanglement is not just the experimental confirmation, but what it reveals about the nature of reality. To understand it, we must imagine that particles don't exist in definite states until they are observed. Before measurement, an electron doesn't have a fixed spin, and a photon doesn't have a definite polarization. They exist in a superposition of possibilities. When two particles are entangled, their combined state must be described as a single, unified quantum system. You cannot describe one without the other, their fates are intertwined. When one is measured, its state is revealed, and simultaneously, the other's state snaps into place, no matter the separation. This isn't communication in the ordinary sense. It is correlation built into the very foundation of the system. To make this more relatable, consider an analogy with a pair of gloves. Suppose you put one glove in a box and send it to New York, while keeping the other with you in Los Angeles. Before opening the box, you don't know which glove is inside. But once you open it and see the left glove, you instantly know the other box contains the right glove. That's not mysterious, it's just common sense. However, quantum entanglement goes far beyond this simple analogy. With the gloves, the left and right were predetermined before separation. In entanglement, the properties are not predetermined. They exist in uncertainty until measured. Only at the moment of observation do the outcomes become definite, and somehow, across any distance, the other particle reflects that choice instantly. This lack of predetermination is what makes entanglement so baffling. The mystery intensifies when we consider what entanglement means for our concept of reality. If the outcome of one particle is undefined until measured, and yet the other particle somehow knows what to become instantly, then reality itself appears non-local. It suggests that space and time may not be the ultimate stage on which the universe operates, but rather features that emerge from a deeper, underlying reality. Some scientists speculate that entanglement could be a clue to understanding the fabric of spacetime itself. Perhaps the universe at its most fundamental level is not built of isolated particles but of relationships, links of information that bind everything together. From a philosophical standpoint, this is astonishing. It undermines the notion of separateness. In our daily lives, we view ourselves as independent beings, distinct from everything else. But entanglement shows us that separateness is, in some ways, an illusion. At the quantum level, particles that were once together can never be fully apart again. They remain connected as though distance is meaningless to them. This raises profound questions. If reality is woven together by such connections, could it be that everything in the universe is, in some sense, entangled? Could the fabric of reality itself be nothing but a vast web of entanglement? The mystery is not just scientific, it's deeply human. For centuries, thinkers, poets, and philosophers have wondered whether the universe is more interconnected than it seems. Entanglement gives us a scientific demonstration of that intuition. It shows us that the hidden truth of the universe is not isolation but connection, and while entanglement is most easily seen in the laboratory, when physicists work with photons and electrons, its implications extend to our understanding of life, consciousness, and existence itself. It suggests that the universe does not divide itself neatly into separate parts, but instead creates a reality where the whole is more fundamental than the pieces. One of the most beautiful aspects of this mystery is how it inspires both humility and curiosity. Despite all our technological progress and mathematical mastery, entanglement reminds us that we do not fully understand reality. We can measure it, predict its outcomes, and even harness it for practical uses, but we cannot yet explain why it works the way it does. The hidden truth of quantum entanglement is that the universe is stranger than we imagined, and it demands from us an openness to mystery. Rather than resisting it, as Einstein once did, we are now called to embrace it, to explore its depths, and to let it reshape our view of the cosmos. Quantum entanglement is not just an academic subject confined to textbooks or laboratories. It is a glimpse into the deeper nature of reality, a truth that lies hidden beneath the surface of everyday experience. To define it simply, it is the phenomenon where particles remain mysteriously linked across space and time. But to truly appreciate its mystery, we must admit that it defies explanation in terms of classical thinking. It forces us to accept that the universe operates on principles that are not intuitive, but are nonetheless real, verified, and profoundly significant. The mystery of entanglement is not a weakness of science, but one of its greatest strengths, reminding us that discovery is about venturing into the unknown and expanding the boundaries of human understanding. In the end, the definition of quantum entanglement is inseparable from its mystery. To describe it is to encounter the limits of language and imagination, for it belongs to a world beyond common sense. Yet that is what makes it so powerful. It reveals that hidden within the smallest particles of the universe are truths that can change the way we see everything, from the nature of space and time to the meaning of connection itself. Quantum entanglement is not only a cornerstone of quantum physics, it is an invitation to marvel at the strange, interconnected reality we inhabit. It tells us that the universe is more mysterious, more beautiful, and more unified than we ever dared to believe. Albert Einstein is remembered as one of the greatest scientific minds in history, a man whose theories redefined our understanding of space, time, gravity, and energy. His work on relativity transformed physics and reshaped the way humanity thinks about the universe. Yet, despite his brilliance, there was one concept he could never fully accept: quantum entanglement. For Einstein, this idea seemed not only counterintuitive but also impossible, something that conflicted with the very foundation of his worldview. His skepticism became a defining chapter in the story of quantum mechanics, and in many ways it added depth to the mystery of entanglement itself. Einstein was deeply uncomfortable with the probabilistic nature of quantum mechanics. The theory suggested that at the subatomic level, outcomes are not determined until they are measured. An electron could exist in multiple states at once. A photon could travel as both a wave and a particle. And reality itself appeared to be a tapestry woven from probabilities rather than certainties. For Einstein, who sought a universe that was orderly, logical, and governed by clear laws, this was unsettling. He believed that physics should describe definite reality, not just the probabilities of what we might observe. This is why he famously remarked, "God does not play dice with the universe." He could not accept that chance was woven into the very structure of existence. When quantum mechanics introduced the concept of entanglement, Einstein's doubts grew even stronger. Here was a claim that two particles could be linked in such a way that the state of one instantly determined the state of the other, even if they were separated by vast distances. For Einstein, this was unthinkable. He argued that this kind of instantaneous action at a distance violated the principle of locality, one of the cornerstones of his theory of relativity. Locality asserts that an object is only directly influenced by its immediate surroundings, and that information cannot travel faster than the speed of light. If entanglement were true, it would mean that something could bypass this cosmic speed limit, undermining relativity itself. To Einstein, this was an unacceptable conclusion. In 1935, Einstein, along with physicists Boris Podolsky and Nathan Rosen, published what is now known as the EPR paper. In it, they presented what they thought was a paradox that would expose the incompleteness of quantum mechanics. They described a scenario where two particles interacted and then separated, yet remained entangled. Measuring one particle would instantly reveal information about the other. To Einstein and his colleagues, this meant one of two things. Either information was somehow traveling instantaneously between the two particles, which violated relativity, or quantum mechanics was incomplete, and there were hidden variables that determined the outcomes in advance. They leaned heavily toward the latter explanation. For Einstein, the notion of hidden variables was more palatable than accepting what he mockingly referred to as spooky action at a distance. The phrase itself, spooky action, captures the essence of Einstein's discomfort. He was a man who had spent his life bringing clarity and order to physics, who had shown how gravity could be understood as the curvature of spacetime rather than some mysterious force pulling at a distance. To then accept a phenomenon that appeared irrational, almost mystical, was something he could not do. Einstein did not deny the mathematics of quantum mechanics. He acknowledged that the theory worked remarkably well in predicting experimental outcomes. But he insisted that it was not a complete description of reality. To him, it was a useful tool but not the final truth. Einstein's skepticism had profound implications. On one hand, it fueled debates among physicists, sparking a tension that would last for decades. On the other, it pushed the scientific community to test the limits of quantum mechanics more rigorously. His insistence that there must be hidden variables led to new lines of inquiry. He challenged others to either prove him wrong or uncover the deeper reality he believed must exist. In a way, Einstein's doubts drove progress, for without them, physicists might not have pursued the kinds of experiments that eventually confirmed entanglement. One of the most fascinating aspects of Einstein's skepticism is how it highlighted the divide between two ways of thinking about physics. On one side were those like Niels Bohr, who embraced the strange, probabilistic nature of quantum mechanics. Bohr argued that quantum theory did not describe reality itself, but only our observations of it. Reality, in his view, was not something fixed and definite. It was something that emerged when we interacted with it. On the other side was Einstein, who could not accept this philosophical stance. He believed in an objective reality that existed independently of observation, one that could eventually be explained by clear and deterministic laws. The clash between Einstein and Bohr was not just a scientific debate, but a philosophical one about the very meaning of reality. Over the years, experiments began to chip away at Einstein's position. In the 1960s, physicist John Bell devised his famous theorem, which created a way to test whether hidden variables could explain entanglement. Bell's inequalities, as they became known, showed that if hidden variables existed, then certain statistical limits should appear in the measurements of entangled particles. If quantum mechanics was correct, those limits would be violated. When experiments were conducted, starting in the 1970s and continuing with increasing sophistication, the results consistently sided with quantum mechanics. The correlations between entangled particles were stronger than anything that could be explained by hidden variables. In other words, Einstein's suspicion that quantum mechanics was incomplete did not hold up under experimental scrutiny, yet even as experiments confirmed entanglement, Einstein's skepticism continued to shape the conversation. Many physicists respected his unwillingness to accept the theory at face value. His insistence on deeper understanding encouraged others to look beyond the equations and ask what they really meant. Some have even suggested that Einstein's resistance to quantum mechanics was not entirely misplaced, because to this day, the true nature of entanglement remains one of the most profound mysteries in science. We can describe it mathematically, we can use it to develop technologies like quantum computers and secure communication systems, but we still struggle to explain why it works the way it does. In this sense, Einstein's demand for a clearer picture continues to resonate. It is also important to note that Einstein's skepticism was not rooted in stubbornness or a refusal to accept new ideas. It was born from his deep commitment to consistency and logic in science. He believed that the universe was ultimately comprehensible, that beneath its complexity lay simple, elegant laws. For him, quantum mechanics felt like an incomplete puzzle, one that gave the right answers without showing the full picture. His resistance was in many ways a testament to his intellectual integrity. He was not willing to embrace a theory that clashed so deeply with his sense of order, even if that theory seemed to work. Looking back now, Einstein's skepticism adds richness to the story of quantum entanglement. It reminds us that even the greatest minds struggle with new ideas, and that skepticism can be a powerful force for progress. It was his refusal to accept entanglement at face value that spurred others to design experiments to test it, and in doing so, they confirmed one of the most extraordinary truths of nature. Ironically, Einstein's attempt to discredit entanglement helped solidify its place as a cornerstone of modern physics. There is also a certain poignancy in Einstein's skepticism. In many ways, his discomfort with entanglement symbolizes the limits of human intuition. We evolved to understand a world of objects, distances, and straightforward cause and effect. The quantum world operates on principles that are utterly alien to this everyday experience. Even a genius like Einstein, whose imagination soared far beyond the ordinary, struggled to accept a reality so strange. His skepticism is a reminder that science is not just about discovery, but also about humility, about recognizing that the universe is often stranger than we can believe. Today, as we continue to explore the possibilities of quantum technology, Einstein's phrase "spooky action at a distance" lives on. It captures the awe and bewilderment that still surround entanglement. We can harness it, measure it, and even use it to reshape technology, but we still marvel at its strangeness. And while Einstein may have been proven wrong in his rejection of entanglement, his skepticism played a vital role in ensuring that the truth was revealed not by assumption but by rigorous experiment and careful thought. In the end, Einstein's doubts did not diminish his legacy, they enhanced it. They showed his human side, his unwillingness to accept mystery without understanding, his deep desire for clarity in the midst of confusion. His skepticism was not a failure but part of the process by which science advances. Through his resistance, he forced physics to confront its own strangeness, and in doing so, he helped illuminate one of the most profound truths of the universe. Quantum entanglement remains a mystery, but thanks to Einstein's questions, we understand it better. His skepticism reminds us that science thrives not only on belief, but also on doubt, not only on answers, but also on the courage to question those answers. And in that sense, Einstein's struggle with entanglement is not a contradiction of his greatness, but a reflection of it. When we think about reality, we are conditioned to see it as a collection of separate, independent parts. Each object seems to exist on its own, with its own boundaries and its own identity. A chair is a chair, a tree is a tree, a person is a person, each distinct from the other. Even in classical physics, the universe was long viewed as a vast machine made up of individual components, each obeying precise laws of cause and effect. But quantum entanglement reveals something that challenges this perspective at its very core. The universe is not simply a collection of isolated pieces, but an interconnected web where relationships can be more fundamental than the objects themselves. This shift in perspective changes how we see physics, philosophy, and even ourselves. Entanglement forces us to reconsider the idea of separateness. In everyday life, distance matters. If you are in one city and I am in another, we are clearly apart. My actions here cannot directly alter your state there, but at the quantum level, this logic does not hold. When two particles become entangled, they are no longer fully separate, no matter how far they travel from one another. Their states are bound together in such a way that they must be described as one system rather than two. It is not just that they influence each other across distance, rather, they share a single quantum state that cannot be broken down into individual parts. This means the very concept of independent objects, so central to our normal view of the world, breaks down in the face of quantum entanglement. To illustrate, imagine you are looking at a painting. You could, if you wanted, focus on the brushstrokes, examining each small line or patch of color on the canvas. But if you only focus on isolated strokes, you lose the bigger picture. The painting is not in the brushstrokes alone, it is in the relationships between them, in the way they come together to create form and meaning. Quantum entanglement suggests the universe works in a similar way. It is not only the strokes of the particles that matter, but the relationships between them. The whole emerges from the connections, not just from the parts. This interconnectedness is not symbolic or poetic. It is literal and physical. When two photons are entangled, their polarizations are linked. When two electrons are entangled, their spins are correlated. No matter how far apart they are separated, their states are tied together in a way that cannot be explained by local properties alone. One cannot talk about the state of a single particle independently. One must talk about the state of the entire entangled pair. This is a profound shift in thinking. It suggests that the universe is not fundamentally composed of isolated entities, but of interdependencies that cannot be reduced to their individual elements. The implications of this are staggering. If particles that were once together can remain linked across distance, then separateness is, in some sense, an illusion. We might think of space as dividing things, but entanglement shows that deep connections can exist that transcend distance. This calls into question our understanding of space and time themselves. Could it be that entanglement reveals something deeper about the structure of reality? Some physicists believe so. There are theories suggesting that spacetime itself, the fabric of the universe as described by relativity, may be built from entanglement. In this view, entanglement is not just a curious phenomenon of quantum physics, but the foundation of everything we experience. Philosophically, the idea of interconnected reality resonates with many traditions of thought. For centuries, spiritual and philosophical teachings have spoken of unity beneath apparent diversity. Mystics from different cultures have suggested that all things are linked in some profound way, even if that unity is hidden from ordinary perception. Quantum entanglement, while purely scientific in its discovery, echoes this ancient intuition. It gives us empirical evidence that connection is not merely metaphorical, but embedded in the structure of reality. In this way, physics and philosophy meet, each pointing to a universe that is less about isolated objects and more about deep, inseparable relationships. The interconnected nature of entanglement also challenges how we think about causality. In classical thinking, causes precede effects and influence moves step by step. If I push a ball, it rolls because of my action. But with entanglement, the instant correlations between particles blur this linear sense of cause and effect. If two particles are separated by light years and measuring one instantly defines the other, then our usual picture of causal chains breaks down. It is not that one particle causes the other to take on a particular state, it is that they are aspects of a single, shared system. Their relationship transcends the framework of cause and effect as we understand it. This pushes us to rethink not only the mechanics of physics, but the very meaning of connectedness in the universe. Consider what this interconnectedness means for the way we view ourselves. We often think of human beings as independent entities, each enclosed in our own body and mind, separate from the world around us. But if reality itself is structured through entanglement, then at the deepest level, separateness is not the ultimate truth. Just as particles cannot be fully described apart from their relationships, perhaps our lives too gain meaning not in isolation but in connection. We are part of a larger whole, threads in a cosmic web that binds us to everything else. This idea does not diminish individuality but enriches it, showing that our identities are interwoven with the universe itself. The interconnected reality revealed by entanglement also reshapes how we approach technology and science. Quantum computers, for example, rely on entangled states to perform calculations in ways that classical machines cannot. The power of these computers comes not from isolated bits of information, but from the relationships between qubits in entangled superpositions. Similarly, quantum communication systems use entanglement to create links between distant locations that cannot be intercepted or tampered with. These technologies harness the fundamental truth that the universe is built on connections, not just objects. In doing so, they transform what was once an abstract mystery into a practical force that can reshape civilization. At a deeper level, entanglement challenges us to see the limitations of our language and concepts. We talk about particles being connected across distance, but in reality, it is not two separate things being linked. It is a single system manifesting in two places. Our human categories of here and there, this and that, are stretched to the breaking point. Entanglement suggests that these categories may not reflect ultimate reality, but are approximations shaped by our limited perspective. The true nature of reality may be far more holistic, with divisions existing only in our minds. This is a difficult concept to grasp, but it reflects the humility science demands. Reality is not required to conform to human intuition. It is also worth noting that interconnectedness does not end with pairs of particles. Scientists have created entangled systems involving multiple particles, even thousands of atoms at once. These experiments show that entanglement is not a rare or fragile oddity, but a pervasive feature of the quantum world. The more we study it, the more it seems that entanglement is not an exception, but a rule. This suggests that the interconnected reality may extend far beyond what we can currently measure. If even large systems can remain entangled, then the universe itself might be a vast network of quantum connections, with everything linked in ways we cannot yet fully comprehend. The psychological impact of recognizing such interconnectedness is profound. For centuries, human beings have struggled with feelings of isolation, with the belief that we are separate individuals navigating an indifferent universe. Entanglement challenges that belief. It whispers to us that separation is not the ultimate truth, that at the deepest level, connection defines existence. Even if we cannot directly perceive it, the physics tells us that the universe is woven together. This realization can shift how we approach not only science, but also how we live our lives, reminding us that our choices, our relationships, and our presence in the world are part of something greater than ourselves. Ultimately, the interconnected reality revealed by quantum entanglement is one of the most important truths we have discovered about the universe. It tells us that separateness is an illusion, that the boundaries we see are not the final word. At the deepest level, reality is not about parts but about wholes, not about objects but about relationships. Entanglement is the scientific doorway into this truth, showing us that the universe is far stranger, richer, and more unified than we once believed. To accept this is to accept that our understanding of reality must evolve, that we must move beyond the comforting framework of independence and embrace the mysterious, beautiful truth of interconnectedness. In doing so, we not only deepen our grasp of physics, but also of life itself, seeing that we are, in every sense, entangled with the cosmos. When we enter the world of quantum mechanics, we leave behind the comforting certainty of classical physics and step into a realm where uncertainty is not a flaw in our knowledge but a fundamental feature of reality. At the heart of this strange new landscape lies the idea that outcomes are not fixed until they are measured, and probabilities replace certainties as the language of nature. Quantum entanglement magnifies this mystery, showing us that uncertainty and probability are not confined to individual particles, but can stretch across space, binding distant objects in ways that challenge our understanding of cause and effect. To expand upon this truth is to face one of the most profound shifts in human thought, the realization that uncertainty is woven into the fabric of existence. For centuries, science was built upon the idea of determinism. Classical physics, shaped by Newton's laws, painted a picture of the universe as a giant clockwork mechanism. If you knew the position and velocity of every particle, you could, in principle, predict the future with perfect accuracy. The past, present, and future were all bound together in a chain of inevitability. This world, you gave humanity a sense of mastery over nature. It suggested that with enough data and the right equations, nothing was beyond prediction. The universe was orderly, and uncertainty was merely a sign of human ignorance, something that could be eliminated with more precise measurement. Quantum mechanics shattered that vision. In the quantum world, particles do not have definite positions or properties until they are observed. An electron is not located at a single point but described by a wave function, a mathematical expression that represents a range of probabilities. Before measurement, the electron exists in a superposition of possible states. When measured, the wave function collapses into a specific outcome, but until that moment, uncertainty reigns. This is not a matter of hidden details waiting to be discovered. It is an intrinsic feature of nature. Uncertainty is not about what we don't know, it is about what reality itself has not yet decided. The Heisenberg uncertainty principle captures this truth in mathematical form. It tells us that we cannot simultaneously know certain pairs of properties with absolute precision. For example, the more precisely we know a particle's position, the less precisely we can know its momentum, and vice versa. This is not due to limitations in our measuring tools, it is a law of the universe. The act of measurement itself disturbs the system, forcing it into one state while closing off others. Reality is, at its core, probabilistic. This principle fundamentally challenges our assumptions about what it means to know something. In the quantum world, knowledge comes in probabilities, not absolutes. Entanglement adds another layer to this mystery. When two particles become entangled, their uncertainties are not independent but correlated. Before measurement, each particle exists in a cloud of probabilities, but the moment one particle's state is determined, the uncertainty of the other vanishes in perfect alignment. If one particle's spin is measured as up, the other's spin will be down, regardless of the distance between them. What is astonishing is that neither particle had a definite spin before measurement. Both existed in superpositions, their properties uncertain, until the act of observation collapsed them into reality. Yet this collapse happens simultaneously for both, across any distance, as though the universe itself is orchestrating the outcome in one seamless gesture. This interweaving of uncertainty and entanglement reveals something profound about reality. Probabilities are not merely statistical tools for human beings. They are the raw material of existence. The universe is not built of certainties that we cannot yet see. It is built of possibilities that only solidify when interaction occurs. The act of measuring one particle in an entangled pair does not merely reveal information about the other, it creates that information, collapsing uncertainty into reality. This suggests that probability is not a reflection of ignorance but a fundamental feature of how the universe works. The philosophical consequences of this are immense. If reality is probabilistic, then the future is not predetermined. Unlike the clockwork universe of Newton, the quantum universe is open, filled with branching possibilities. The world is not a script being read line by line. It is a dynamic play where the ending is not written until the moment it unfolds. This realization changes how we think about free will, destiny, and the nature of time itself. If uncertainty is fundamental, then creativity and spontaneity are built into the cosmos at the deepest level. At the same time, the role of observation in collapsing probabilities raises questions about the nature of reality itself. Does reality exist in definite form only when it is measured, or is there some deeper mechanism at work that ties probabilities to outcomes? Some interpretations of quantum mechanics, such as the Copenhagen interpretation, suggest that reality does not exist in a definite state until observed. Others, like the many worlds interpretation, propose that all probabilities are realized in branching universes, and what we perceive as collapse is simply our experience of one branch. Still others argue for hidden variables, though experiments inspired by Bell's theorem have largely ruled out local hidden variable theories. Whatever the explanation, the undeniable fact is that uncertainty and probability are not illusions, they are the foundation of the quantum world. Entanglement deepens this puzzle because it shows that probability is not confined to individual particles, but extends across space, binding objects into shared uncertainty. Before measurement, the entangled system exists in a combined state, a superposition of possibilities. Measuring one particle does not just reduce its uncertainty, but instantly reduces the uncertainty of its partner. This suggests that probability is not local but global, woven into systems that cannot be divided into independent parts. Reality is less like a collection of isolated dice being rolled and more like a vast interconnected game, where the outcome of one roll is inseparably tied to another, no matter how far apart. This picture also transforms how we think about information. In the classical world, information is definite. A coin is either heads or tails, and knowing one outcome does not change the other. In the quantum world, information exists in superposition, and entanglement means that information can be shared across distance in ways that defy classical logic. The collapse of uncertainty into certainty is not merely a local event, it is a global reconfiguration of probabilities. This has practical consequences, giving rise to the possibility of quantum communication and computation. Quantum computers, for instance, exploit superpositions and entanglement to perform calculations that classical machines cannot, effectively using probability itself as a resource. Quantum communication uses entangled states to share information in ways that cannot be intercepted without detection. In both cases, the uncertainty that once seemed like a limitation becomes a source of power. Beyond technology, the embrace of uncertainty also has a profound psychological and philosophical impact. For centuries, human beings have sought certainty as a source of security. We long for clear answers, definite truths, and predictable outcomes. But quantum mechanics tells us that certainty is not the essence of reality. Uncertainty is. This can be unsettling, but it can also be liberating. If uncertainty is fundamental, then possibility is infinite. The universe is not a fixed and closed machine, but an open field of potential. This means that mystery is not a temporary obstacle, but an eternal feature of existence, inviting us to explore and discover endlessly. One way to grasp this is to reflect on how probability shapes our everyday lives. Even outside physics, our experiences are filled with uncertainty. We make choices without knowing the outcomes, we take risks, and we navigate a world where the future is never guaranteed. Quantum mechanics suggests that this uncertainty is not just a quirk of human life, but a mirror of the universe itself. Our lives echo the fundamental structure of reality, where possibilities unfold into actuality through interaction and observation. In this sense, the uncertainty we experience is not separate from the uncertainty of particles. It is part of the same cosmic dance. There is also something profoundly humbling in the realization that uncertainty is built into the universe. It reminds us that human knowledge, no matter how advanced, will always be limited. We can calculate probabilities with extraordinary precision, but we cannot eliminate uncertainty itself. This humility keeps science honest. It forces us to recognize that the quest for understanding is not about finding final, unchanging answers, but about deepening our grasp of a reality that is dynamic, unpredictable, and alive with possibilities. And yet, uncertainty does not mean chaos. Quantum mechanics is not random in the sense of pure disorder. The probabilities follow precise mathematical rules, described by the wave function and governed by the Schrödinger equation. The outcomes of quantum experiments may be uncertain, but the statistical patterns are consistent and reliable. In this way, uncertainty is structured. It is not a breakdown of order, but a new kind of order, one that blends unpredictability with mathematical harmony. This paradox, uncertainty within order, is one of the most beautiful aspects of quantum physics, reminding us that reality can be both unpredictable and intelligible at the same time. In the context of entanglement, this structured uncertainty takes on an even deeper significance. The correlations between entangled particles are not random. They are perfectly aligned according to the rules of quantum mechanics. The uncertainty of one particle is balanced by the uncertainty of the other, and when one collapses, the other collapses in harmony. This shows that uncertainty itself is not isolated but relational. It is not just about what one particle can or cannot know, but about how particles share uncertainty across the universe. This interdependence of probability suggests that reality is not a collection of separate uncertainties, but a unified field of potential, where outcomes are woven together in a cosmic fabric. Ultimately, to expand on the truth of uncertainty and probability in quantum entanglement is to recognize that our deepest intuitions about reality must evolve. The universe is not a predictable machine, but a realm of possibilities. Certainty is not the foundation of existence, uncertainty is, and far from being a limitation, this uncertainty is what allows for creativity, freedom, and transformation at every level. Entanglement shows us that this uncertainty is not isolated but shared, stretching across space and time, binding distant particles into a common fate. The hidden truth of quantum mechanics is that probability is not an approximation of reality, it is reality. To embrace this is to embrace the mystery and beauty of a universe that is forever unfolding, never finished, and endlessly full of possibilities. When we consider the technological impact of quantum entanglement, we are not simply speaking about a theoretical curiosity or a strange quirk of physics that belongs in the classroom or laboratory. We are, in fact, exploring the seeds of a technological revolution that could reshape the world as dramatically as electricity or the internet once did. Quantum entanglement, once considered a bizarre and almost philosophical dilemma, has slowly moved from the realm of abstract theory into the arena of practical application. It holds within it the potential to transform communication, computation, cryptography, sensing, and even our understanding of what technology itself means. This is not science fiction or distant speculation. It is the frontier of science today, where probability and uncertainty are harnessed to create systems that defy the limits of classical technology. To grasp why quantum entanglement carries such profound technological implications, we first need to understand its core property. When two or more particles become entangled, they share a connection that goes beyond the limitations of space and time. The measurement of one instantly determines the state of the other, regardless of how far apart they may be. In the laboratory, this has been demonstrated countless times, with entangled photons and electrons revealing correlations that cannot be explained by classical physics. What this means in practical terms is that entanglement allows information to be linked in ways that traditional systems cannot replicate. Instead of information being localized, it becomes distributed, shared across distance in a way that seems instantaneous and unbreakable. One of the most direct technological applications of entanglement is in the realm of communication. Classical communication relies on signals, whether radio waves, light pulses, or electrical currents, that travel through a medium and can be intercepted or degraded. Quantum entanglement, however, opens the door to what is often called quantum communication. By sharing entangled particles between two parties, information can be encoded in the correlations between measurements. If one party measures their particle, the outcome is instantly related to the outcome of the other, creating a secure channel of communication. What makes this remarkable is that any attempt to intercept or measure the entangled particles by a third party will disturb the system and reveal the intrusion. This property gives rise to the concept of quantum key distribution, a method of encrypting messages that is theoretically unbreakable. Nations and corporations are investing heavily in developing such systems, seeing them as the foundation of a future where secure communication is not merely an aspiration but a guarantee written into the laws of physics. China, for instance, has already launched satellites that use quantum entanglement to enable secure communication between distant locations. This is not science fiction, it is reality. Experiments have shown that entangled photons can be transmitted from orbit to Earth, surviving the journey and maintaining their correlations. This demonstrates the feasibility of building a quantum communication network that spans the globe. Imagine a world where financial transactions, government communications, and personal data are shielded not by human-made algorithms that can eventually be broken, but by the fabric of quantum mechanics itself. In such a world, eavesdropping would be not merely difficult but impossible. The very act of attempting to observe the communication would expose itself, ensuring transparency and security. Another transformative field shaped by entanglement is quantum computing. Classical computers, no matter how powerful, operate by processing bits that are either 0 or 1. Their strength comes from speed and parallel processing, but they are ultimately limited by the binary nature of information. Quantum computers, by contrast, harness the power of quantum bits, or qubits, which can exist in superpositions of 0 and 1. Entanglement allows these qubits to be linked, creating a system where computations are performed across vast combinations of possibilities simultaneously. The result is a machine that can, in principle, solve certain problems exponentially faster than classical computers. For example, tasks like factoring large numbers, which form the basis of much of modern encryption, could be solved in moments by a sufficiently powerful quantum computer. Problems in optimization, drug discovery, material science, and artificial intelligence could be tackled in ways that are impossible with today's technology. Entanglement is the glue that enables these qubits to work together, ensuring that their probabilities are not independent but connected in ways that yield coherent solutions. Without entanglement, quantum computers would be little more than probabilistic calculators. With it, they become engines of discovery capable of reshaping industries and societies. The practical development of quantum computers is still in its early stages. Companies like Google, IBM, and startups across the world are racing to build scalable machines that can operate with thousands or millions of qubits while preserving their fragile entangled states. The challenges are immense, involving issues of decoherence, error correction, and stability. Yet the progress made in recent years is staggering. Demonstrations of quantum supremacy, where a quantum computer performs a task impossible for a classical machine, have already been achieved. While these tasks are still narrow and specialized, they point to a future where entanglement-driven machines could become as commonplace as laptops or smartphones, fundamentally altering the technological landscape. Beyond communication and computation, quantum entanglement is also revolutionizing the field of sensing and measurement. Classical sensors, no matter how precise, are limited by the noise and uncertainty inherent in their design. Quantum sensors, however, use entanglement to push beyond these limits, achieving levels of precision that were once thought unattainable. For instance, entangled particles can be used to measure time with extraordinary accuracy, leading to atomic clocks that redefine the standard of precision. These clocks have applications not only in scientific research, but also in GPS technology, telecommunications, and global infrastructure. Imagine navigation systems that are accurate down to the centimeter, or communication networks synchronized with perfect precision across continents. These are not distant dreams but foreseeable outcomes of entanglement-based technology. Similarly, quantum sensing could transform medical imaging, geological exploration, and environmental monitoring. Entangled photons can be used to peer through barriers that classical light cannot penetrate, creating imaging systems with unprecedented clarity. Quantum gravimeters, devices that measure gravitational variations with extraordinary sensitivity, could help locate underground resources or detect tectonic shifts before they cause earthquakes. Entanglement thus becomes a tool not only for abstract experiments but for practical systems that touch daily life in profound ways. Perhaps one of the most intriguing aspects of entanglement's technological impact is its ability to redefine what security means in the digital age. Today, much of our digital security is based on mathematical complexity, algorithms that are difficult to solve with current computers, but may become vulnerable with future advances. Quantum entanglement shifts the foundation from mathematical assumptions to physical laws. Security is no longer a matter of being ahead in the arms race of algorithms, it becomes a property of reality itself. This could usher in an era where trust in digital systems is not tentative but absolute, transforming how societies operate in a digital world. Of course, the promise of entanglement is matched by challenges. Maintaining entanglement over long distances and extended periods is extraordinarily difficult. Quantum systems are fragile, easily disrupted by interaction with their environment. Decoherence, the process by which quantum states lose their coherence and collapse into classical outcomes, is a constant obstacle. Building practical technologies that rely on entanglement requires ingenious engineering, from isolating particles in ultra-cold environments to developing error-correcting codes that preserve quantum information despite inevitable disturbances. The progress being made in these areas is remarkable, yet the hurdles remain daunting. There are also profound ethical and societal implications. If quantum communication becomes the norm, how will governments and corporations handle a world where information is unbreakably secure? If quantum computing can crack classical encryption, what happens to the vast stores of data already encrypted with current methods? How do societies prepare for a technological shift that could disrupt industries and reshape economies? The answers are not simple, but the questions themselves reveal the magnitude of the transformation entanglement could unleash. At a deeper level, the technological impact of entanglement forces us to reconsider our relationship with knowledge and power. Throughout history, new technologies have shifted the balance of societies, from the printing press to electricity to the internet. Entanglement-driven technologies could represent the next such shift, creating opportunities for progress but also risks of inequality and misuse. Will quantum technologies be used to empower humanity collectively, or will they become tools of dominance wielded by a few? The decisions we make in developing and deploying these systems will determine whether entanglement's potential becomes a gift to all or a weapon of the powerful. What is undeniable is that entanglement is not confined to the chalkboards of physicists. It is shaping real, world technologies with consequences that will echo across generations. The world we inhabit in the coming decades may be one where communication is unbreakably secure, computation is unimaginably powerful, sensing is exquisitely precise, and security is rooted in the laws of nature. In that world, uncertainty and probability, the very features of quantum mechanics that once baffled us, will become the engines of progress. Entanglement, once mocked as spooky action at a distance, will be the foundation of a new technological era. As we stand on the threshold of this transformation, it is worth remembering that every great technological revolution begins with a strange and improbable idea. Electricity was once invisible fire, magnetism a mysterious force, the internet a wild dream of global connection. Entanglement is today's improbable idea, already blossoming into tomorrow's reality. The question is not whether it will change our world, but how, and how soon. To explore its technological impact is not to peer into a distant fantasy, but to look directly at the unfolding future, a future where the hidden truths of quantum mechanics are not merely understood but lived, shaping the fabric of human society and the destiny of our civilization. Quantum entanglement does more than transform science and technology. It reaches into the deepest recesses of human thought, raising questions about the nature of reality, the boundaries of knowledge, and the meaning of human existence in a universe that is both mysterious and interconnected. For centuries, philosophy and science walked hand in hand, each shaping the other. When quantum mechanics entered the stage in the early 20th century, it did not just give us new equations or clever experiments. It challenged the very categories through which we interpret the world. Entanglement, in particular, forces us to rethink ideas of separateness, causality, time, and even consciousness. In exploring its philosophical and human implications, we come face to face with questions that are as old as civilization, yet renewed with astonishing urgency by discoveries at the smallest scales of matter. At its heart, entanglement undermines the idea that the universe is composed of independent, self-contained pieces. Classical physics led us to believe that objects exist with definite properties, interacting through forces transmitted across space and time. Entanglement shows us a different picture. Reality is not made of isolated parts but of relationships. Two particles that have interacted and become entangled are no longer separable in any meaningful sense. Their identities are tied together in a way that persists even when they are separated by vast distances. This interdependence suggests that the fundamental unit of reality is not the particle but the connection. To speak of one particle alone is to miss half the story. It is only in their relationship that the full truth emerges. Philosophically, this resonates with ancient and spiritual traditions that have long emphasized interconnectedness. From the Buddhist idea of dependent origination to the mystical teachings of unity in diverse religious traditions, there has been a recurring intuition that the universe is a web of relationships rather than a collection of separate entities. Quantum entanglement gives scientific form to this intuition, grounding it not in poetry or metaphor but in experiment and mathematics. The universe, it seems, is a network of possibilities woven together, where boundaries are far less rigid than they appear. This realization carries profound human implications, inviting us to reconsider not only our understanding of physics, but also our place in the cosmos. One of the most profound challenges posed by entanglement is to the notion of causality. In everyday life, we assume that causes precede effects, that events unfold in a linear sequence governed by time. Entanglement scrambles this intuition. When one particle is measured, the state of its entangled partner is determined instantaneously, regardless of distance. This appears to defy the speed limit set by the speed of light, creating what Einstein famously called spooky action at a distance. While this does not allow for faster than light communication in the conventional sense, it nevertheless reveals a form of correlation that transcends classical causality. It raises the possibility that our notion of cause and effect is incomplete, that there are deeper patterns of connection that underlie the unfolding of events. This has implications for how we think about time itself. In a classical worldview, time is a steady river, flowing from past to present to future. Quantum mechanics, however, suggests that the distinction between past, present, and future may be less clear than we imagine. Entanglement correlations seem to exist outside ordinary time, as if the universe holds a deeper layer of order where temporal sequence is not the ultimate organizing principle. Some physicists have even proposed that entanglement might be more fundamental than spacetime itself, that the fabric of reality could be woven from entangled connections out of which space and time emerge. If this is true, then our human experience of time as a linear progression may be only a surface phenomenon, an approximation of a more intricate and timeless structure. For the human mind, such ideas can be both unsettling and inspiring. On one hand, they challenge the assumptions that structure our lives, assumptions about individuality, about the flow of time, about the certainty of knowledge. On the other hand, they open a vast horizon of possibility, suggesting that the universe is more mysterious, more alive, and more interconnected than we ever dared to dream. Entanglement becomes not just a scientific concept, but a mirror reflecting the limits of our imagination and the need to expand our ways of thinking. Another dimension of entanglement's philosophical impact lies in its challenge to realism. Do particles have definite properties before we measure them, or do those properties exist only in the act of measurement? The Copenhagen interpretation famously suggests the latter, implying that reality is not fully real until it is observed. This gives rise to provocative questions. What does it mean for something to exist? Does reality depend on consciousness? Are we co-creators of the universe, collapsing possibilities into actuality through our observations? Some interpretations push back against this idea, insisting that reality exists independently of us, but the experimental evidence leaves the question hauntingly open. Philosophers and physicists alike wrestle with this mystery, aware that it touches on the very boundary between the subjective and the objective, between the observer and the observed. This leads naturally to one of the most daring questions entanglement raises. What is the role of consciousness in the universe? Some thinkers have speculated that consciousness itself might be entangled, that the unity of awareness we experience may be linked to quantum processes in the brain. While such ideas remain speculative and controversial, they reveal the hunger for a deeper understanding of how mind and matter are connected. If reality at its core is relational and probabilistic, then consciousness, too, might be woven into that relational fabric. Whether or not this proves true scientifically, the very fact that entanglement raises the possibility highlights its capacity to blur boundaries we once thought were firm between matter and mind, between physics and philosophy. On a human level, entanglement speaks to our experience of connection. We live in a world that often emphasizes individuality and separation, where people are treated as isolated entities pursuing their own goals. Entanglement reminds us that at the deepest level, nothing exists in isolation. We are part of a web of relationships, physically, biologically, emotionally, and perhaps even spiritually. Just as entangled particles share a state across distance, human beings are entangled in bonds of culture, history, language, and shared experience. Recognizing this interconnectedness can inspire humility and compassion. It challenges the illusion of separateness that often drives conflict and division, pointing instead toward a vision of humanity as a network of interwoven lives, each influencing and shaped by the other. There is also a profound lesson here about uncertainty. Classical thinking sought certainty and control, imagining a universe that could be mastered through knowledge. Quantum mechanics shows us that uncertainty is fundamental, not a flaw but a feature of existence. Entanglement amplifies this by demonstrating that uncertainty is not confined to individuals but shared across systems, linking outcomes in ways that cannot be predicted with certainty. For human beings, this is both a challenge and a gift. It challenges us to let go of the illusion of absolute control, to embrace the unknown as part of life, and it gifts us with the possibility of openness, creativity, and discovery. Just as quantum probabilities give rise to the richness of the physical world, human uncertainty gives rise to the richness of human experience. In practical terms, the philosophical implications of entanglement are already shaping debates in ethics, politics, and society. If quantum communication creates unbreakable security, what does this mean for transparency and power in human institutions? If quantum computing can crack current encryption, how should societies prepare for the vulnerability of their data? If entanglement shows us that separateness is an illusion, how should this influence how we treat one another and the planet we share? These are not abstract questions. They are urgent and real, demanding wisdom as well as technical knowledge. Entanglement teaches us that the boundaries we draw between self and other, between nation and world, between present and future, may be less fixed than we imagine. To ignore this lesson is to miss the chance to align our societies with the deeper truths of nature. Perhaps the most profound human implication of entanglement is the sense of wonder it awakens. In a world often driven by pragmatism and utility, entanglement reminds us that mystery is alive. The universe is not fully knowable, not reducible to equations alone, but always more than we expect. This wonder is not childish or naive. It is the wellspring of curiosity, creativity, and awe that has driven human beings to explore, to question, to dream. Entanglement shows us that even in the most precise and rigorous science, wonder is unavoidable. The cosmos is stranger, more beautiful, and more interconnected than any of our stories, and to live with that awareness is to live more deeply. It is worth remembering that philosophy has always been about more than abstract thought. It has been about how we live. If entanglement reveals that reality is relational, uncertain, and interconnected, then the human task is to live in harmony with that reality, to cultivate relationships, to embrace uncertainty, to recognize our interconnectedness with one another and with the universe. To do so is to align our lives with the hidden truths of nature, to embody in daily action the insights that quantum mechanics has revealed in the laboratory. In the end, the philosophical and human implications of quantum entanglement cannot be confined to physics or philosophy. They reach into art, literature, religion, and the very way we imagine our lives. They call us to humility, reminding us that the universe is greater than our certainties. They call us to responsibility, reminding us that our lives are entangled with the lives of others and with the fate of the planet. And they call us to wonder, reminding us that mystery is not something to be solved once and for all, but something to be embraced as the essence of existence. To expand upon these implications is to recognize that entanglement is not just about particles in a lab. It is about what it means to be human in a universe that is deeply, irrevocably, mysteriously connected.